Welcome back to this module on exploiting DLP using SIMD instructions. In this lesson I will describe the data alignment problem and how it can be solved. In addition, I will describe data reordering instructions that reorder or permute the elements in a SIMD vector. In almost all SIMD ISA, an n-byte SIMD vector must be aligned at an n-byte boundary. That means the address must be, the byte address must be a multiple of n. If we access data at an unaligned place, then we need two aligned accesses. We need to shift these two arrays and then we need to merge them. How do we deal with misalignment? Either we can say the programmer or compiler has to do it. Unfortunately, very often alignment is a runtime restriction. For example, if we access a subblock of a larger block, so very often then the programmer has to deal with it. Or we can deal with it with an OS exception. Or we can do it in hardware. Several instruction set architectures allow unaligned accesses, but these accesses are very slow because the element or the vector, the SIMD vector, it may be split over two cache lines. And so we need two cache accesses and they have to be merged and aligned somehow. For example, examples of unaligned memory access instructions SSE. SSE we had move double Q quad word aligned. This indicates aligned, whereas SSE2 supports also move double quad word unaligned. MOV move double quad word unaligned, which may also be used, but which is much slower than the move double quad word aligned. So which is best depends on the particular situation. Also, in many applications, in many media applications as well as other applications, from time to time we need to reorder the elements in a vector to make them amenable to SIMD processing, which only processes consecutive elements in parallel. This is supported, data reordering is supported in different ways, can be and is also supported in different ways. We can use full permute instructions, which have some disadvantages that I will discuss later. We can use mixing, unpacking, merging. We can use align and rotate, and we can use insert and extract. And I will now discuss these approaches, these different ways of supporting data reordering one by one. The simplest, perhaps the simplest, is the full permutation. So permutation is the most powerful reordering operation, but also the most costly in terms of hardware and most likely also in terms of time. For example, Ultifac supports the vperm with 4 operands instruction. And this means that we select byte elements from the vectors of VA and VB by the byte index given in VC. In other words, we have a parallel loop where VDI, element I of VD, is set to the concatenation of VA and VB, which is indexed indirectly by VCI. And please check this example here, how this permutation realizes a full data reordering. Another possibility is to restrict the number of permutations that are implementable in hardware directly, and then more general permutations need to be implemented on top of these. The simplest example is perhaps interleaving. also called mixing, also called unpacking, also called merging. The previous unpack instructions that I illustrated a few slides ago can also be used to implement data permutations that are very common in media applications. For example, matrix transpose. In media applications, we often have to perform an operation on all rows in parallel as well as all columns in parallel. And therefore, transposing the matrix makes a lot of sense. Also, to go from the usual color band interleaved ordering, that's how red, green, blue pixels are usually stored in memory, to band separated ordering, which is more amenable to SIMD processing. So this is typically how images are stored in memory. First the red color component, then the green color component, then the blue color component of a particular pixel, then again red, green, blue of the next pixel, and here we have another segment of the pixel. Then we can use the unpack operation to move it to a somewhat more band separated form, where first we have the red values, then the green values, and finally the blue values, and some two red values remain at the end of the 8-element vector. Another operation which is extremely useful for supporting unaligned memory accesses is to support align and rotate operation. Align and rotate operation shift the data in two source registers by a specified number of bytes. And it's useful for aligning unaligned data, but the usefulness for other permutation operations, for other reordering patterns, is very limited, if at all present. For example, SunFiz extension supported an instruction called align data. This instruction took the address of two instructions and placed of two vectors and placed the start address of the first cache line in one register and the offset in another register. Then we could load V1 and V2, and then we could execute the align data instruction, which would put these two elements together in one vector. The problem for the SunFiz was that the operands of align data were implicit, so no reordering, no out of order reordering, no superscalar execution was allowed after align data has been executed. The fourth and final data reordering operation that has been implemented in multimedia SIMD instruction set architecture extension are insert and extract. Insert means that we insert a scalar subword at a specific vector position in a vector register. Extract means that we take out or extract a subword from a specific vector position. This is of course very general. We can implement any permutation on top of these extracts and inserts. However, an arbitrary general permutation will require n of these extracts and inserts, where n is the vector length in terms of number of elements, not in terms of bits. Here's again an example. Here we extract the third element from V1 and put it into R1. And the reverse operation is insert, where we insert the scalar value in R1 to the fifth element of vector 2. This completes this lesson. Thanks for watching. In the next lesson I will discuss two different ways of supporting control flow in SIMD instruction set extensions. Hope to see you back.